Okay, so what we have is the beginning of a single replacement reaction. We should be able to finish this. Okay? So let's try to do that. All right, again, it all starts with assigning oxidation numbers and doing the same thing over and over again. So today is about figuring out whether reactions can occur, whether a redox reaction can occur. And I can do that by using something called Table J or net potentials. Today we're going to predict and understand why a redox can or cannot occur, but again, it starts from the same skills. So, I've got a single replacement reaction trying to get started. What's going to happen? Now think with me for a second. We're going to try to replace tin with copper. All right? In fact, we've had a lab. If you remember, we had copper chloride with aluminum. So we've seen this before. Yes?
I have this. It says writing half reaction.
That's not the same one, is it? It's a different one. Got to say the same one. That's why I asked him. Okay? Now, in order for copper to jump in here, single replacement means that we're going to replace the copper with tin. Right now, the tin is staying with the chlorine. Why? Why does the tin stay with the chlorine? Tin, by the way, is SN. Lead, it's, not lead. It's Roman, I guess, for tin is stannum, okay? The Latin word. Okay, so chlorine is what charge, if it has to be negative? What's the only negative choice for chlorine?
-1.
-1, correct. Now there's 2 of them overall, so it's -2 overall. So what charge must tin be?
2.
It must be +2 overall to equal 0, but because there's only one tin, it's +2 individually. Remember, I use the what? The bottom numbers to get to the top. What's the charge in the copper? Standalone. 0. Good. Now, after assigning oxidation numbers, guys, now look at this. The tin is staying with the copper, chlorine. Why? What charge is it? It's attracted to the chlorine. It's +2. The only way for copper to get in there is that copper's got to get charged positively, and tin has to lose its charge. So what happens here, party people, is a redox reaction. Copper, who's a standalone element, who does what? What do standalone metals always do? They lose their electrons, correct. So my friends in chemistry, copper, if this works, should give 2 electrons to the tin. The tin becomes tin 0. Once it becomes an atom with no charge, it's not going to be attracted to the chlorine anymore. And it comes off. After the copper loses 2 electrons, it's going to become copper +2. And when it's +2, it's going to attract the 2 chlorines, who are -1 apiece. So what we're looking, guys, is at the details of a single replacement reaction. We're explaining why this works. We've looked at these already, but now we're looking at the details. So, half reactions. Now, the question is, does this work? What I'm saying to you is, if I have some copper, let's put some copper here. For those that don't know copper, I've got copper and tin up here. Copper's got this golden color, so or copper color, depending on how you want to look at it. And tin has a more silver, luster-y kind of a flare to it. Okay, so I'm going to get rid of the tin for a second, and I'm going to make some tin chloride. So tin chloride. Now tin is not a transitional element, so it's not going to have a colored solution. And our copper is right here. So I'm going to put the copper in the tin solution, and we're going to see if a redox reaction occurs. Before we do that, let's go to the half reactions. Okay? Let's go to the half reactions. First of all, let's start with the oxidation. Who's getting oxidized? Who's changing here? Yeah, Cu. Copper 0 is going to what? Copper plus? Yep. Now, how many electrons are involved in this exchange? 2. So where do they go? And the check is what? That both sides of a half reaction have the same, right, are equal, same charge. So where do I put the 2 electrons? Redox side. I need 2 of them, so I have 2e negative. And I know that's correct because a -2 and a +2 is 0. This is a 0. Good stuff. Okay, now, the next one, who's changing? Do I write chlorine down here?
No.
No, because chlorine's neither getting oxidized nor reduced. Its charge is staying the same. So, I start with the tin. Tin, what charge? Plus 2. Now, what does it become? 0. Right. Now, the question is, how many electrons are involved here? 2. And now, where do I put them? Reactant side. So, both sides have the same charge. Hint. The check is you put the amount of electrons that make both sides equal to each other. And if you've got electrons on the product side on one side, you better have electrons on the reactant side of the other. Someone's losing, someone's gaining. Copper is giving his electrons to the tin. The tin accepts the 2, becomes 0 charged, and no longer can be attracted to the chlorine and comes off. Copper, who becomes plus 2, should jump right in there, okay? And then you get your Singer replacement, at least theoretically. I don't know if it works. We're going to get to that. Now, quickly, from yesterday, who got reduced? Specifically, substance reduced. Now, the tin implies, that's tin.
Oh, no.
You want to say specifically tin. It's a nice place to go in the summer. Have you been there? Tin plus 2? It's probably a nice place to go anytime. Tin is plus 2. Who specifically had oxidized? Cu plus 2 or Cu 0? So by saying copper, you imply the element. So copper is good or Cu. Okay, agents. Who is the oxidizing agent? Here, agent, think opposite. The tin plus 2. If I am the oxidizing agent, I myself get reduced. Who's the reducing agent? Okay, this is everything we've done so far. Now here comes the new stuff. I want to know if this actually works. I want to predict whether this reaction actually works. And this is what we do. Now, I can give you table J, which make no sense to you, and give you some rules. I'm going to show you where table J comes from. Okay? So you've got a net potential table. Okay? And I want you to look at it. And we're going to look at it together. Let me explain it, okay, for a second. Now, you'll see table J on one side. You'll see net potentials on the other. Okay, maybe not. Wrong one. So I want this one. Here we go. This is what we're looking at. Now this is where table J comes from. Now let me explain what this is all about. Now if you notice, what kind of half reactions are being written to the left of everything there? Now this, accepting electrons or giving? Am I absorbing or gaining electrons, or am I losing in all these half reactions? Gaining, so they're all what? They're all written as reduction. Okay, now let me explain. A voltage represents a potential difference. Now let me explain. A voltage is nothing more than the energy that pushes the current, let's say in a wire. In your house you have wires that carry electricity. The reason why electricity is nothing more than charges being flown. If I have a place that's very, very negative and a place that's very, very positive, electrons want to flow. That's called a voltage. Okay, potential difference, a difference of high charge to low charge. Think of a waterfall. Higher the waterfall, the higher the force on the water crashing down. That is what voltage is. If I want to create a voltage, I create a difference in charges. And basically, like anything else, things want to go from high to low. So if electrons are in two positions and both have the same charge, electrons don't flow. But if I change the difference in charge from a place of high negatives to a place of low negatives, electrons want to flow. If I make the height of my what? Waterfall higher, water flows downward with more force. So voltage is a potential difference. What it really is a pathway. Higher the voltage, the better that something can do something. In this case, we call it spontaneity. But let's pretend lithium plus E is a negative voltage. Negative voltage means that's how much energy you have to add to make that happen. I want to go backwards up a what? Waterfall. I have to add energy. If I go down the waterfall, I don't have to add energy. I can ride that energy pony downhill. Okay? So anything negative voltage means that that's what I have to add to become, to go this way. These guys hate to get what? Reduced. Now think with me, it's kind of like delta H. If I'm terrible at getting reduced, I must be good at what? Gaining. I'm losing. I'm bad at gaining electrons, I must be good at oxidizing. Who's the best at getting oxidized? This would be positive 305. Who's better at oxidized, lithium or potassium? In the reverse, lithium is positive 305. In the reverse, potassium is positive 292. Let's go to the bottom of the table. Okay, this will make sense. Just trust me. Trust me. Give me a chance here. Okay, now watch. In the bottom of the table, who's really good at gaining electrons? That gives a huge positive volts. Are you surprised? Fluorine is the most electronegative atom we have. It loves to attract its own electrons and fantasize about gaining some more. Fluorine loves. How about oxygen? That's why we call it oxidation. If you have oxygen, it pulls electrons from metals. That's why we call it oxidation. Notice who's next. Fluorine, bromide. Are we going down the hill? Bromide isn't as what? Electronegative. Okay, so we have fluorine, chlorine, bromide, iodide. We're going down the group of the halogens. Now, forget all that. What about this one? Does gold Au plus 3 like to gain electrons?
Yeah.
Gold plus 3, that's called aurum, the Latin name for gold, loves to gain 3 electrons, which means it does what pretty bad? It's pretty bad at losing electrons. Gold doesn't oxidize very well. That's why it stays shiny. They think gold was the first metal discovered in rivers because it was glimmering. It never rusts because it hates to lose electrons. That's why we make connectors in gold for any kind of contraptions that we want contacts metal to metal and not oxidize. Okay, very important. Okay, look where silver is. Silver doesn't like to oxidize, but it's not as resistant as gold. Who's better than these two? What the metals? Let's go higher. Who's better? Who's better at oxidizing? Look at copper. Isn't copper better at oxidizing than silver and gold?
Yes.
What about cobalt? What about lithium? So what you have here, guys, is a list of metals that show how well they oxidize. Who's on top? Who's on top? Lithium, cesium, potassium, rubidium, barium. Who's on the bottom? Who's the worst metals at oxidizing? Well, yeah, but fluorine's not a metal. The worst metal is what? Gold. Who's next? So now, watch table J. Where do you think they get this from? Who's the worst metal at oxidizing? Right. Who was second? Right. Who was on top on my other chart? Who was on top? Lithium, right? So they give you how well metals are active. Metals lose electrons. Metals are good at what? Oxidizing. This list is how well nonmetals are good at what? Reducing. Did I tell you that fluorine was the best? Then it was chlorine, bromide, iodide. We're going down the halogens. This terrible table came from net potentials. But we're going to do something with it. I'm going to show you how you use it, but we're going to do it the real way. Okay. What's my first reaction? Okay? My first reaction is I want to take copper and I'm going to put it in tin chloride. Let it sit there for a little bit. Now watch. Let's go look at the voltages. Now, back to our reaction. What's our reaction? Pay attention. Oh, Christmas in July. Where are you? Okay. So where's my reaction? I need copper to do what for this to work? It needs to what? Give off electrons. It needs to what? Oxidize. Let's go find the volts for copper oxidizing on this. So now, I go to my table. No, not that one. Go to my table, and I'm going to find copper. Now watch. Copper oxidizing. Let's see, we'll scroll this up. Okay, copper oxidizing is right here. Now, copper oxidizing to 2 plus 2 would be going this way, correct? So what do I do with the charges? Yeah, so this would be negative 0.34, which means it doesn't go that way. It's climbing uphill. So negative 0.34 that way. Put it next to it. Negative 0.34. Okay? So we put negative, where am I? There we go. Negative 0.34 volts. What does negative mean? It doesn't like to do that. That's the energy you have to put in to make it happen. It's not spontaneous. You're climbing the what? You're trying to climb. You're trying to ride a boat up a waterfall. Now, tin oxidizing. Let's do that one. I'm sorry, tin reducing. Tin is gaining. So let's go find tin plus 2 gaining 2 electrons and find that voltage. Let's go find tin plus 2. There it is. Now, this one will be as written, won't it? Tin plus 2 gaining 2 electrons. I'm not flipping the sign because it's written as a reduction, so I keep the sign. So it's negative 0.14. Probably can see what's going to happen here. So negative 0.134. Here it is, negative point, what's that, 14?
Yes.
My long-term memory's gone at this time. Okay, now I want you to do for E0 cell, all you're going to do, party people, is you're going to add the 2 voltages together. Well, you're adding 2 negatives, so the overall thing is negative. This becomes an 8. This is 0.48 volts. More importantly, it is negative 0.84 volts. By it being a total negative voltage, what does it scream to you? It's not going to work unless I add energy to it. Is it spontaneous? Spontaneous means does it work? No. So you would say no. The negative volt says it does not. So you would say no. Okay, and I'll put it right here. No! So what that means is my reaction should be doing nothing. Now what's the reason? What's the high-level reason? The high-level reason is copper cannot replace tin in tin chloride. Copper is not a strong enough what agent to make tin plus 2 go 0. It's not good enough to do what? Force its electrons on the tin plus 2. It's not good of a reducing agent. It can't force its electrons onto the what? Tin very well. All right? Tin doesn't like to, think about it. For tin to reduce, you need 0.14 volts. This guy's negative 0.3 volts. So you need a collection of total negative 0.48 volts to make this happen. That's what electrolysis is. Electrolysis is like that. Okay, so this doesn't work. Now, let's go to table J, because I'm going to tell you right now, on the Regents, you don't have to do this. But this makes sense. Watch how I do it in table J. Let's go to table J. Let's do the same thing. Now, go into table J. Let's do that. Now, on this list of activities, metals who are better at oxidizing are on top. Now, who was oxidizing in my problem? Copper was trying to oxidize, correct? So I'm going to circle copper, which is on the bottom here. I'm going to circle copper. Copper was what? Oxidizing, or at least we're trying to make it oxidize, correct? And tin was trying to get what? Reduced. Let's think about this for a second. I have these 2 metals here, correct? I was trying to make copper oxidize when tin is better at oxidizing. Higher the metal, the better you're at oxidizing. I'll say it again. I was trying to make copper oxidize in the presence of tin, but tin is better at oxidizing than copper, so it won't work. So here's how you use table J. The metal who is oxidizing should be on what position compared to the one reducing? If this is a list of who's better at oxidizing. Right, you figured it out. I didn't even tell you. Perfect. The one who oxidizes has to be above the one who reduces to get positive volts. Let's look at my table, net potential table, and see the same thing. Perfect, guys. Exactly. So stay there. Okay? So let's go here again. let's circle what was happening. We had copper plus 2 right here. Copper plus 2. And we had what else? Tin plus 2. Here's my two half reactions. Let's draw directions. Who's better at oxidizing? Tin was, right? Yet I had copper trying. Works the same way. It works the same way. If I want this to be positive, the one who is going to oxidize has to be above. Because in the reverse, this will be positive volts. Higher the metal on this chart, the more positive it will be. Okay? So let's go to the second one. We're going to move a little quicker now because we know how to do this. All right, watch. Now, this is the exact opposite. So now I'm going to take pure tin in copper chloride. Notice the copper chloride is a different color, yeah? And we're dealing with tin, pretty metal. Tin is one of my favorite metals. Molybdenum is my favorite because I like saying molybdenum. Okay, but tin is my favorite. Okay, now, what happens here, party people? What charge is the tin? It's a standalone metal. 0. What charge is the chlorine? The copper must be, in this case, plus 2. What are the products if this works? All right, we're going to tin chloride. So tin is now plus 2. Chlorine plus pure what? What gets kicked out? Copper. Tin is going to be plus 2. Chlorine's negative 1. Copper is a standalone. What's going to happen if this works? Tin is going to force electrons onto the copper. Copper plus 2 gains them and becomes pure copper. And once it becomes pure copper with no charge, it's not attracted. This guy becomes attracted and they switch. This is the details of what you learned. So here we go, party people. SN0 goes to SN plus 2. How many electrons are involved? Where do they go? Products, so that both sides have the same. Say it like you're from New England. Charge. Charge. Okay, now, copper plus 2 goes to what? Copper is 0. Where do electrons go if both sides have to have the same charge? Reactants. Hello. Who got reduced? Cu plus 2. Don't say Cu because you're implying this guy. I'll see you after school. Don't pick anybody from this side. Who got oxidized? Tin 0. Oxidizing agent's the one who gets reduced, right? SN0 is the reducing agent. Okay, what are my potentials now? Well, pretty simple stuff here. Oops, I didn't want to do that. Okay, I got a line that goes nowhere. Okay, let's do tin oxidizing first. So let's go find that. Tin oxidizing. So tin oxidizing, boom. So wait a minute, tin oxidizing is doing this way, right? What's the charge? It's negative as written this way, but oxidizing means you're going this way. Positive 0.14. Uh-huh, mm-hmm. Oh, no, he didn't. Okay, yes, positive 0.14. What must be the copper if it's reducing? Copper reducing as written. Copper plus 2 reducing as written is positive 0.34. It's going to work. So it's positive 0.34, and then we add the voltages together, and we get a positive 0.48 volts. Is it spontaneous? Which means, does it work? And you say, yes. This will work. Let's go see. Let's put the copper, or I'm sorry, the tin, pure tin 0, into the tin plus 2. Now, what's going to happen, party people, if you look carefully, is the tin will go into solution and become tin plus 2. So the solution will eventually look like this, get white and cloudy, and the solution will lose its color, And we're going to make pure what? Copper. Where do you think the copper is going to be plated first? Who is giving the electrons? So when the copper plus 2 hits the tin metal, that's where it gives the electrons. So if I pull this up right now, we should see copper plating the tin. And that's a spontaneous process. Why is it spontaneous? Because it works. Because you saw it work. At least till then. So this is copper on the tin. Solid copper. Okay? So, go back to table J. Can we answer this question another way? Who are the metals involved? Let's get rid of this. Let's make this bigger. Who are the metals involved? Tin and copper. In the second reaction, who was being oxidized theoretically? Tin was being oxidized. And who was being reduced? So the one oxidized is above the one who reduces. That will give me positive volts. So based on table J, you don't have the voltages to do on the test anymore, but you see how table J works. Anytime the one who oxidizes is the one over the metal who's getting reduced, you'll have positive volts. So let's go do the second one. Now we're not going to do voltages anymore. Watch. Let's go on to the second one. Here's a question I have for you here. Can tin replace iron in iron chloride? What do I mean by that? Watch. Can tin, now tin is what? Sn, replace the iron in iron chloride? What am I really asking? Who's going to oxidize? Who are you going to make? Tin is going to replace the iron to make tin chloride. Plus what's going to be free? Iron. Is this a redox reaction? What do you see? Standalones. You guys are understanding this. Great stuff. Now my question to you is, does this work? Can it replace? So the one who oxidizes better be what? Over the one who is getting reduced. Is tin above iron? No. Tin is not above iron in table J. Or is it? No, it's not. So the answer is what? For those that don't see that. For those that don't see that, look. Table J is, get rid of this one. Tin is going to oxidize, and we're going to say that iron is going to reduce. No way this works. The one who's better at what? Oxidizing has to be above to get positive volts, like I just showed you. So this does not work. Now, if you don't see it, too bad. No, if you don't see it, write half reactions. What would you get? Tin 0 going to tin plus 2 electrons, and you'd see, oh, that's oxidizing. Oh, this is plus 2 going to plus 0. That means iron plus 2 is gaining 2 electrons. How about the next question? Can tin replace gold?
Yes.
Why can tin replace gold?
Because tin is higher than gold.
But what does it mean? That means I have tin by itself, and I have Au chloride. Can you see that must mean that has to be Au? Can you see that the tin has to oxidize to be positive to get in here, and this guy has to reduce to accept it to get out? So is tin higher than gold in table J? And the answer is yes. If you don't believe me, you go to table J. Tin is higher than gold. Everything's higher than gold. That's what makes gold so expensive, is it doesn't oxidize. It stays shiny forever. So that does work. Okay, for work of home, I want you to take the worksheet that says standard reduction table J, where it says table J prediction side only. I want you to use table J with the thought in mind that it came from voltages. You don't have to do any voltages for me in this course. My people going next year to the AP will pick that up. But table J prediction aside, that's what I want you to do for work at home. Do you see how this connects? Good stuff. I'm getting great responses. I'll see you tomorrow. I have some more to show you, but do it tomorrow.